everyone and welcome to the lecture 8 of the course Advanced Structural Analysis. We have basically discussed the concepts of the energy approach. We have identified the preliminary requisite for the course which typically we take up in the structural analysis, and now we would like to introduce the method of the indeterminate system analysis. While doing this, we will also take up that the methods are similar to the approach of the matrix method, which typically is the focus of this given course. So, while we are introducing the force and the displacement method for the indeterminate system analysis, we will also see them from the viewpoint of the flexibility and the stiffness approach in the given system. So, the very first method which we try to discuss here is the force method. We will try to introduce the standard force method, consider the standard cases of the release structure and the redundants in the given system, and then we will try to see that what are the basic steps in the analysis. While doing so, we will see that the given content can also be represented in the form of a simple flexibility of the given system. So, the force method was originally developed by the J.C. Maxwell and the O.C. Moore somewhere around the similar time, but independently. The method is suitable for identifying the unknown forces of the given system. So, the primary unknowns which we consider for the force method are the reactions of the given system, and that is also one of the reason of calling it as a force method, because our primary unknown parameters become the forces for the given system. The method uses the conditions of the compatibility as the extra conditions to solve these unknown number of the redundant forces, and that is why the method is also called as the compatibility method. And the given system of the force method, when we apply on the given systems, we typically introduce the unit amount of loads active, and corresponding to that, to define the consistent deformation, we describe the condition of the compatibility of the deformation systems, and this is done by identifying the displacements due to these unit loads on the given problem. So, as we introduce the definition of the displacements with respect to the unit load in the given problem, the method also introduces the flexibility coefficient, and that brings us to say that the method is also a flexibility method. So, in general, the method, the force method, the compatibility method or the flexibility method or approach, these are all the similar names and identified to the basic concept of identifying the reactive forces in the given system. Now, to understand the basic concept of the force method, we will try to see a simple example. We have a simple problem in which a fixed ended beam on both the sides is subjected to some external load. If we consider initially the system is statically indeterminate, so we have a degree of static indeterminacy for the given problem which can be evaluated. If we consider that the axial deformations are negligible, they are not included. So, at both the ends we have two amount of reactions, one translational and the second moment reaction of the given system. And with respect to these four unknowns in the given problem, we have only two equilibrium equations, which are the summation of the forces along the summation of the forces along the y and summation of the moment about the z axis being 0, and that brings us to say that the degree of static indeterminacy in the problem is 2. Now, at the same time, we can identify that the degree of static indeterminacy, this consideration is important to know the forces of the given system. So, as long as we will talk about the forces, we will be looking at the static equilibrium of the given system. We will always try to take up the root of the degree of static indeterminacy, because it typically identifies the available number of forces with respect to the equilibrium equations of the given system. In the second part, we will try to see the conditions of the displacements or the conditions of the compatibility of the given system, and we will realize that the displacements can be identified from the root of the degree of kinematic indeterminacy, and that is what the standard displacement method gives us. So, over here now, as we consider that the given system is subjected to some load and we understand that the system is statically indeterminate with degree 2, what a user can do as a first step, we can reduce this problem into a statically determinate problem, which means that out of all those 4 number of reactions in the given system which are making the system indeterminate, we will try to remove any of the 2 reactions and consider them as the redundants or the extra reactions of the given system, so that the system can be converted into a simple statically determinate problem. Now, there could be multiple ways to do it. One simple idea of this is that I consider, say, at the joint A the support is remaining fixed, whereas at the joint B I have removed the condition of the support. I have removed the fixed support, and now there is no reaction which is being considered at the support B. The second possibility could be that I can just do the reverse of it. I can keep the support at the point B and leave the support A without any of the reactions over here. One more possibility could exist, that could be the providing the pin jointed supports at both these positions, and this will be defining that there is no moment reactions considered at the ends of the given system, and they have been considered as the redundants. One can be further more audacious. I should not put the plus sign, but it is simply that these are the representative systems which are typically being represented as a statically determinate system of this original problem. One more system could be there which is a little bit more audacious to define, and in that we can say that if I remove the reactions, the two vertical reactions of the given system, and now consider the remaining ones as the redundants, and this will define a system support like this, which is the guided roller with only the possibility of the moment reactions, and that is what will have the two redundants on the given problem, which are now the reaction of R1 and R3 for the given problem. Now, one can understand that not all of those systems are possible. The reason being because if I apply some load on the system number 4, the system will not be able to hold these external loads, because the system is not going to get any reactions from these two supports of the given problem. So, though the basic idea of generating a standard statically determinate system is by removing the number of reactions from the given system which are over and above the available equilibrium equation, but while doing so we should also consider that the given system is stable and which is able to feasibly able to take the loads of the external system. Now, at the same time, while we convert the given problem into the statically determinate case, we understand that the solutions 1, 2 and 3 are still feasible, which means that it is not a unique system which will be defined as a statically determinate system, but rather there could be multiple choices which different users can make. So, we understand now out of these given systems we need to select any one of the cases. Say for example, we initially considered that R4 and R2 to be considered as the redundants of the given problem, and that is where we have considered a simple system which is considered with respect to the pin jointed supports and the external load on top of it, and this is the system which we are considering as the release system. We call it as a released statically determinate system, and this is the first point with which we try to reduce the given problem. Now, as we have considered the statically determinate problem having the load, I cannot say that this is the same system as the original problem. What is missing from this given problem is the condition of the two redundants R2 and R4 which have been removed. So, to accommodate them in the further system, what we can do, we can again consider the same system, the same statically determinate system, and now we can consider that R2, which is the unknown redundant or the unknown reaction of the original problem, has been provided to this given system, and we consider this now as the external load to the given problem. So, the idea is that we will be considering some of the reactions which are over and above the degree of the static indeterminacy or the available equilibrium equations. We consider these forces or these reactions as the unknown set of forces in the given system, and we remove them from the basic system initially, and we consider them as the external load active on the statically determinate system. As a next step, I can further go and I can define the third system, in which the second part of the force, which is the reaction at the point B, has been included, and this is the R4. So, the moment we are able to now add these two unknown set of forces R2 and R4 and consider that these external reactions of the original system are being considered now as the external load of the given released or the statically determinate problem, we are somewhere able to make the given three set of systems cumulatively similar as the original problem. But while we are saying that cumulatively similar, we must also say that these are statically similar to the original problem. What we mean by this statically similar is that at the given system, which is the determinate system as we considered the release system 1, the system 2 which is the determinate system subjected to the first redundant, the system 3 which we considered subjected to the second redundant. Now, if we consider say the joint A of the given problem, we realize that the joint A here will have some reaction value. over here also it will have some reaction value in the vertical direction. I can say that the possibility of this vertical reaction at the support A in the original release system 1, in the position of A the reaction at the system 2 of the release structure, and at the position of A the reaction in the vertical direction in the system 3 is cumulatively together added, and this should be same as the actual reaction R1 of the given problem. In the same manner I can define the reaction at the support B of the given problems, and I can say that the cumulative net reaction which I am going to get at these three systems should be equal to the external support reaction which is there in the original system. At least I have the provision, or I have a possibility to consider that the three systems together added will be able to generate a reaction which is defined also in the original problem. When I go with the second components of the R2 and R4, I realize system 1 is not having any possibility of the moment being provided here. System 3 also is not having any possibility of the moment being provided here, considering that these are the pin jointed parts. System 2 is also not having any of the reactions being generated here, but as we have applied the R2 as external load active on the given system, by together adding these three systems cumulatively, I will be able to add the R2 as a unknown set of force at the end of the given system A in the given problem. At the same time, when I add these three systems together, I will also be able to get R4 at the end of the cumulative system B of the given problem. That means once someone is trying to add these three systems together, one is able to get some value of the reactions in the vertical direction at the two supports, one is having a possibility of the two unknown set of reactions R2 and R4 at the ends of the given system, and the original system's load which is provided in the system 1 is also included in the given system, and this system is same as the originally defined problem, at least in the static manner of the given system. That means in terms of the forces, this given system and the original system are same, and I can say that the original given problem has been reduced into these three reduced problems which are defined for the statically determinate system. What typically we have not defined over here and what we have not ensured is the kinematic compatibility of these systems, and now once we are able to define the kinematically similar systems for all these three cases, we will be able to fix the criteria to evaluate the R2 and R4, which are the two unknown values of the reactions of the given system. So, what we mean by the kinematically similar, when we look at the original system, we realize that at the point A the slope and the deflection is 0, whereas at the system B or at the support B the system has having the deflection as well as the slope 0 for the given problem. Now, when I look at the given problem with respect to these three systems, with respect to the external load, I may have a possibility of some slope appearing at this position. When I go with the system number 2, due to the moment being applied here as external load with the value R2, I may have some possibility of the moment or the rotation being provided here, and when I go with the system number 3, I may have a moment of R4 being provided at the joint B, which may also give a possibility of the rotation at the joint A. Now, when I add together the amount of the rotation at the joint A due to the system 1, amount of the rotation at the joint A due to the system 2, and amount of the rotation at the joint A due to the system 3, I have not ensured that these three summations should actually give me the 0 value, because that is the actual amount of rotation available in the original problem, and this gives us the classifying condition that theta in the original problem should be seen, and that theta should be equal to theta due to the system 1, theta due to the system 2, and theta due to the system 3 at the given point. As we have considered the same criteria for the joint B, we can write it as that theta for the point B can be written as theta at the point B due to the system 1, theta at the point B due to the system 2, and theta at the point B due to the system 3. We realize that these are the two conditions which we consider as the conditions of the compatibility, because these are providing the necessity of the displacement profile which is to be provided in the original problem, similar to the three systems which we are trying to represent as the equivalent system of the original problem. So, once I am able to ensure these two conditions and say that theta A has to be 0 and theta B also be 0 as per the original condition. So, the summation of all these three rotations with respect to the system 1, system 2 and system 3 at the point A, and same with the system 1, system 2 and system 3 at the point B, I can ensure that the summation of these 3 values should be equal to 0, and that will give us the condition to evaluate the unknown set of 2 forces which are R2 and R4 in the given condition. So, knowing these values, we can evaluate the unknown set of forces in the given problem, and this typically becomes the standard way of identifying the force method in the given problem. So, as we define the basic steps in the given analysis, we understand that first we identify the condition or the degree of static indeterminacy for the given problem. If we say that the system is having n number of degree of static indeterminacy, corresponding to this, from the original system we remove n number of reactions of the given system. We have seen right now only the external reactions being removed because it was a simple beam problem. In the cases of the trusses or in the cases of certain members where the internal indeterminacy is also available in the problem, we need to remove the internal members or the internal unknowns of the given problem as well. So, by removing the unknown set of reactions of the given system, we convert the given problem into a statically determinate problem, and we call that as a release structure. While we are doing the calculation or we are defining the release structure, we have to ensure that the release structure is stable, and at the same time we also understand that the release structure choices are not unique and there could be multiple set of systems which could be defined by the different users. Once we have got the release structure in the given problem corresponding to the given set of original displacements which we want to generate, we evaluate the deformation in the direction of each of those redundants which have been removed from the given system. So, if the initial indeterminacy of the system is defined n, corresponding to the release system, we have removed n number of forces or the reactions of the given system. These all forces are called as the redundants because we consider that these are the extra conditions available with the given system. So, in the direction of each of these redundants, we define the amount of the displacement with respect to this statically determinate system. The release system will be evaluating the amount of displacements in the direction of the redundants of the given problem. This is the contribution because of the loading of the given system. It could be the rotation at the point A, it could be the rotation at the point B of any given system, it could be the deflection if the deflection happened to be in the direction of some forces, so which are considered to be redundant. So, accordingly these values will be evaluated and we typically label them as the deformation due to the external load. At the same time, we release one by one all the external redundants on the given problem and we consider them to be active on the given system as a unit load of the given problem, and with respect to those loads we apply the again set of deflections in the direction of these redundants, and that we define as the amount of displacements due to the redundants of the given problem. So, we can calculate the displacement or the rotation at any given point with respect to the redundant values. We can calculate the same rotation at the position of the B with respect to the redundant, and this typically is described as delta R in the given problem. And now we understand that the summation of the overall displacements with respect to the load and the redundant contribution should be satisfying the actual conditions which are provided in the direction of those redundants, and those are the compatibility conditions. So, we say delta is equal to delta due to the loading component plus delta due to the redundant components in the given system, and as we know the original conditions of the given supports, we can define these compatibility criteria and then we can define the number of available equations which are same as the original number of defined redundants of the given problem, and we can solve them for the unknown set of forces or the redundants of the given problem. So, this is a standard approach which we typically follow to evaluate a standard force method. We will now see this using some simple examples in the given system. So, as we define this simple example, we consider that there is a problem in which we have considered a multi-span continuous beam subjected to some loading. We considered initially that in order to consider this system into a simplified form, we have removed all these set of reactions from the given problem, because these are all the set of extra reactions which are over and above the available equilibrium equation, and I can consider the simple statically determinate system as a simple cantilever beam which has been considered here. So, this is the release structure which is of course stable, and we have applied the external load on top of it, but as we have considered the original problem with respect to which we have some values of the reactions at say the joint 1, joint 2, joint 3 and up to joint n of the given problem, we one by one add these n systems in the given problem in which we apply the amount of the reaction, the unknown reaction value of the given system at each of the joints of the given system. So, as a first part, we add the redundant value of R1 in the position of the load 1, which is over here. Then we add the position at the position of the reaction 2, the unknown value of the force, which is R2, and we consider that these are all the external loads, but these are unknown values. So, we have still a determinate system on which we are applying some load values which are unknown for the given system. Now, as we consider the first system, we understand that the system will have some deflection, say the deflection profile will be identified like this. At the position of the 1, we will have some amount of displacement which we call as displacement at the position 1 due to the external load. Now, with the same system, I can calculate the deflection at the point 2 and I can call it at the deflection at the point 2 due to the external load. Similarly, I can keep on doing this for all the n number of points and I can define displacement at the position n with respect to the external load of the given system. As I am going with the second system where the redundant R1 is applied as external load on the determinate system, we consider the deflected profile, and now as the R1 value is not known to us, it is an unknown value for the given system, we consider this load to be 1 unit in the given problem. And as we apply the unit load in the given system, corresponding to that we evaluate the value of the deflection over here, which is delta at the position 1 due to the R1. Similarly, delta at the position of 2 due to the R1, and similarly over here delta at the position of n due to the R1 of the given system. We have considered that the value of the load is 1 unit, and that is what gives us the similar definition of the flexibility which we defined earlier. I can do the same exercise for the given system of R2, where I define the deflection profile again, calculate the deflections at the individual systems of the given problem, this value being delta at the position of the 1 due to R2, this delta at the position of 2 due to the R2, and similarly this delta at the position of n due to the R2 of the given system. And similarly, we can keep on doing this for all the n values of the loads in the given system, and that will give us the respective deformation profile of the given system. Now, as we want to define the compatibility conditions, we typically define the compatibility in the direction of the selected redundants. So, we have R1, R2 and up to Rn selected redundants of the given problem. So, when we want to define the condition of the compatibility in the direction of the redundant 1, we consider that in the position of the R1 there is a vertical support provided. That means this system in the original point should not have any deflection over here. That means the condition of the deflection at position 1 is known to the user, which is equal to 0, and now this delta 1 should be actually same as delta 1 due to the external load, delta 1 due to the redundant 1 plus delta 1 due to the redundant 2, and similarly up to delta 1 due to the redundant n in the given problem. As we have provided the values of these redundants with unit magnitude, we can actually consider them in the similar definition of the flexibility which we initially take up in the given system. So, with this criteria in mind, we can do this kind of compatibility conditions for all those set of displacements which are in the direction of these redundants identified in the original problem. So, at the position of the redundant 1, I describe the displacement, adding the displacement for all these n systems, I add the contribution, which is like this. Along with that, we also add the contribution due to the external load. Similarly, at the position of the R2, we describe the component of all the displacements and we add their contribution that should be equal to the actual displacement in the original system, and these cumulative sums give us the primary criteria of the given compatibility condition. We can describe these n compatibility conditions for the given system. As we have already defined that the individual value is considered 1 unit, so corresponding to that I can describe the expression in this form, where individual components like this, they appear as the simple coefficients of the flexibility. So, if this coefficient we define, this is delta 1 with respect to R1 equal to 1 unit, and we call it as f of 1 1 in the given problem. Similarly, if I just go to this particular component which is with respect to delta 1 with R2 being 1, I can define this as f of 1 2 in the given system. So, displacement at the position of the redundant 1 with respect to the unit value of the load applied at the position of the redundant 2 in the given system. With this idea in mind, we can finally write the expressions in this simple manner, which typically describes all the n number of systems with respect to their conditions of the flexibility matrix coefficient and the respective values of the loads. Now, as a representation of this given system, we can consider that while evaluating the values of delta 1 with respect to the load, delta 2 with respect to the load, we need to consider the simple external load system as the real work system of the given problem. Whereas, when we need to evaluate the standard values of the flexibility coefficients, we need to consider these individual systems for analysis. Now, to take a simple example, let us go with the calculation of delta 1 L in the given problem. We understand that delta 1 L, which is the deflection over here, is due to the external load which is applied on the given problem. It may be possible that the external load is not directly active at the same point. So, we need to make a virtual system with a unit load at this position, and for this given problem we already have this given system which is applying the unit load at the position of the reaction 1, and that is considered as the virtual system for the given problem. So, I consider now these all unit load systems as the virtual system, and corresponding to that the given system of the loading is the real system of the given problem. Now, if I want to calculate the deflection at the point 1 due to the external load, I can calculate it by considering that the given system will give me the external work done, which is the amount of the force into the displacement over here, which is 1 delta 1 into L, and this should be equal to the virtual strain energy associated with the given system, and that is equal to m star into d theta. As we realize, m star has to be with respect to the virtual system, whereas d theta should be with respect to the real system. The virtual system over here is the system due to this one. So, we define this value as the m1, the moment distribution due to the system which is the virtual one, and the real system is the original loading system. So, we describe the m dx upon EI for this loading system as the primary consideration. If we do this part for all the different systems, so this is for the calculation of the displacement with respect to the node 1, I can do this with respect to any generalized node I of the given problem. In that condition, the m1 will be converted into m of I, whereas the remaining part of the expression will remain same. So, I can describe that any particular component delta I with respect to the loading is described by this given expression. We can keep on doing the unit load applications at the different positions of these redundants and calculate the amount of the deformation due to the external load in the direction of these redundants of the given system. Now, in order to define the flexibility coefficients of the given problem, one can define that the flexibility coefficient describes like f of ij is the displacement in the direction of the redundant I due to the unit load in the direction of the redundant j. Now, in order to define this value, as we consider, say for this given case, I want to evaluate the corresponding value of the given system, the f of 1 in the given problem, I will realize that I am going to apply the load in the same direction. So, this system will be considered as the real system for which I am doing the calculation. Whereas, if I want to calculate corresponding to the same load, the displacement in the position of the system 2, which will be considered as f of 2 then this will be requiring me to have a virtual system also in place, and this will become the virtual system in that condition. So, for most of the computations which are being done for the flexibility coefficients, we go by the standard idea of the consideration of the real and the virtual system. We consider that there is a generalized system where we are considering the load is applied at the position of the j. So, this is the real system where the load is being applied, whereas the displacement is being calculated at the position of the ith redundant of the given system. So, this is the position at which I require the actual load. So, that is why we have come up with a virtual system at which we have applied the unit load in the position of the ith redundant. Now, this is the virtual and this is the real system. I can define the moment distribution in this system as m of I for the given system, whereas the moment distribution in this can be described as m of j for the this could be described with respect to the ith joint. So, this is m of I and this is m of j for the given system. Now, as I want to describe the corresponding value of the displacement f of ij, the external work done will be 1, which is the load, into the displacement which is delta over here due to the unit load at the position of the j. So, this will describe f of ij, and this should be equal to m star into d theta. M star is for the virtual system. So, this is what we have defined as the m of I, and m or the d theta is for the real system. So, this has been defined with respect to this parameter, and this comes out as mj dx upon ei. So, we can describe any generalized flexibility coefficient by this simple expression which identifies the flexibility of the given problem. So, this is the generalized expression which can give us the individual coefficients of the flexibility by considering all these systems which are subjected to the unit load in the direction of the different redundants. Now, as a simple example case, we consider a problem over here. We have a system subjected to the external load. As an initial case, we consider that the system is considered with this release structure. In this release structure, we consider that this is having some moment distribution as m. This is our first system in which we consider that the redundant one which is being considered, and we apply it with the unit value. So, this is the unit moment in the given condition. In the system 2, we also consider this as a unit moment. So, this is the system 2 which we considered for the given problem. At any given position x away from the given end of the problem, we consider the amount of the moment in all these 3 cases, and that moment can be described capital M for the real or the release system, the M1 for the first redundant system, and M2 for the second redundant system of the given problem. Now, as we want to define the conditions of the compatibility, the conditions of the compatibility will be with respect to the redundant 1 and redundant 2, which will be the rotation at the position of the support A and the support B. So, we describe it as theta 1 which is the rotation at the point A, theta 2 which is the rotation at the point B is equal to the rotation because of the external load, rotation because of the redundant 1, and rotation because of the redundant 2 in the given system. This simplified equation can also be written as a simple vector form where we write theta 1 and theta 2, and we describe them as theta 1 and theta 2 due to the external load, and then the flexibility coefficients can all be arranged in a simple matrix form which we describe like this, and we multiply this value with the available values of the redundants of the given system. With this kind of a expression, we come up with this definition of the simple flexibility matrix of the given system in which all the flexibility coefficients have been arranged. R becomes the redundant which is unknown to us. Flexibility coefficients can be evaluated based upon the expression which we have just seen, and the displacements or the rotations in the direction of the given redundants due to the external load can also be evaluated. So, once these values are known to us, the flexibility coefficients are also evaluated, we can solve the given condition of the compatibility to know the unknown values of the redundants in the given problem. So, as we go with this problem, we realize that the values of the expressions which we typically define for all the cases can be known. The theta 1 which is with respect to the external load is defined as m1m dx upon ei, which is corresponding to the first system. The theta 2 with respect to the external load is defined with respect to the m2 system. So, this is the second parameter, and these are the flexibility coefficients as described for the given problem. We can recall that these all expressions are based upon the same criteria which we derived in the previous slide. Now, once I move forward, I can consider the value of the moment which is with respect to the given system. I have taken the x axis from here, and corresponding to that the moment value is described. We have considered that about any given axis the positive direction of the moment are described like this. So, if I consider this WL by 2, so the moment WL by 2 into x is positive, whereas the downward load is giving minus of WL square upon 2. Similarly, with respect to these reactions with the unit amount of the moment at the two ends, we can describe the value of the moment m1 over here and m2 with this given system. Once we have all these values, we can substitute them in the given expression, and we can calculate the standard values of these expressions, and from there we can have the values of these parameters of the given system. Theta 1 as we originally understand in the given problem is 0, and theta 2 which is also corresponding to the original system is 0 for the given problem, and that give us the given expression for evaluation of the R1 and R2 in the given system. That R1 and R2 can be evaluated as the inverse of this given matrix So, we can just describe this inverse of this given matrix in the given problem into the multiplier of this given system, and once we take the system on the opposite side, it will come with the negative sign. So, it can be written as 1 upon EI WL cube upon 24 WL cube upon 24. So, with this point we can evaluate the values of the unknown redundants of the given problem. So with this we stop over here. We have briefly seen the basic methods, basic steps of the force method. The energy approach becomes much more helpful to evaluate these set of deformations. We have seen a systematic approach to define the flexibility coefficients of the given system. And as a rider on the given problem, we understand that the choice of the redundants are not very unique, and the ease of the computation is much influenced by the choice of the redundants which a user takes. With this we stop over here. Thank you everyone.